is designed to cycle the refrigerant from liquid to gas and then back to liquid again indefinitely. It does this using pressure and heat. 4 primary components make up a sealed cooling system: an evaporator, a compressor, a condenser, and a capillary tube. The component that absorbs heat from the air is the evaporator. It's placed in the freezer, where the greatest amount of cooling is required. The evaporator is simply a long, narrow tube compacted into an efficient size. Refrigerant enters this tube as it changes phase from a warm liquid to a cold gas at around -20 degrees Fahrenheit. As it travels through the tubing, it absorbs heat from the air flowing over it. The air becomes cold, and the refrigerant becomes warm. By the time it leaves the evaporator at the other end of the tube, it is around room temperature and can absorb no more heat. But the air that flowed over the evaporator is now very cold and can be distributed throughout the refrigerator. The refrigerant, on the other hand, is of no use unless it can be converted back to a liquid so that it can change phase to a gas again, absorbing more heat. To convert it back to a liquid, we must either lower its temperature below its boiling point or raise its boiling point above its temperature. Since we can't lower its temperature all the way to -20, we temporarily raise its boiling point by increasing the pressure. The refrigerant is drawn from the low-pressure evaporator into the compressor. The compressor takes this low-pressure warm gas and moves it to the condenser. The condenser is also a long tube compacted for efficiency, but it's much smaller than and cannot hold as much refrigerant as the evaporator. As the compressor continues to force refrigerant into the smaller condenser, the refrigerant compresses into a very hot gas. Compressing the refrigerant raises its boiling point well above the current room temperature, but it also increases the total temperature, so it is still in a gas state. As hot refrigerant travels through the condenser tubing, the cooler room temperature air around it absorbs some of the heat from it. Refrigerant exits the condenser still warm. We use that to our advantage and run a loop around the cabinet opening, where it will gently warm the surface, preventing any moisture and mold buildup. By the time the high-pressure gas reaches the end of the post-loop condenser, it has cooled to approximately 100 degrees Fahrenheit, passing below the new boiling point that we created, and thus changing from a gas back to a liquid. We are now ready to drop its boiling point back down below the temperature so that it will boil again, changing phase from a liquid to gas, absorbing heat. A tiny capillary tube is placed between the condenser and the evaporator that controls the drop in pressure. The size and length of the cap tube are carefully calculated to restrict flow at a rate that keeps the pressure high in the condenser and very low in the evaporator. When refrigerant leaves the capillary tube and enters the much larger evaporator tube, the drop in pressure instantly lowers the boiling point and the temperature back to its original point. The refrigerant immediately begins changing phase from liquid to gas, absorbing heat from its environment. It's now back to the beginning of the cycle. This cycle continues indefinitely. The condenser is a critical component of a sealed system. It must be capable of removing heat from the hot refrigerant. To do that, it must stay free of dust and dirt. If a blanket of dust collects on the condenser, it will prevent it from giving up its heat to the surrounding air. How often the condenser must be cleaned depends on its design and construction. Both are superior on frigid air. There are 2 types of condensers: natural draft and forced air. Static or natural draft condensers have been in use for many years. This type of condenser spreads the tubing across the back of the refrigerator and relies on the natural properties of heat rising and air circulating within the kitchen to transfer heat from the refrigerant. Dynamic or forced air condensers have been in use for many years. The condenser tube is folded into a tighter space and placed underneath the refrigerator. Dynamic condensers rely on a fan to create enough airflow to remove heat from the refrigerant. Air is drawn in the front through the tow grill on the left-hand side, then travels through the carefully engineered condenser and harmonically balanced condenser fan. It then moves over the compressor and escapes out the tow grill on the right-hand side. The compressor is like the human heart to a cooling system. It's every bit as important to the proper operation of the cooling system. It can't miss a beat. A compressor is basically an electric motor and a pump. Its sole purpose is to pump refrigerant throughout the arteries of the sealed system. The shell is hermetically sealed, or airtight, and is mounted on 4 sound-deadening rubber grommets. Refrigerant is drawn in from the low-pressure or evaporator side, where it has just absorbed the heat from the surrounding air. It leaves the discharge heading toward the high-pressure side, or condenser. The heart of the compressor is its electric motor, consisting of a stator, a rotor, and a shaft. The stator contains copper windings and applies a magnetic field to the rotor and shaft, causing them to turn at 3,400 RPMs. This is the electric motor. The rotor and shaft drive a piston back and forth in the compression cylinder. The piston draws refrigerant into the cylinder on its pull stroke and forces refrigerant out on its push stroke. The piston employs a patented design that increases efficiency by directing the refrigerant toward the exhaust valve. This is the pump action of the compressor. As the piston strokes back, the pull that it creates draws refrigerant in from the evaporator through the suction muffler. The suction muffler reduces the noise refrigerant makes flowing into the compressor. As the piston pushes forward, the exhaust valve opens and refrigerant heads out toward the condenser. When the exhaust valve opens, refrigerant exits the cylinder through 2 small ports and enters the exhaust mufflers. This exclusive feature increases efficiency beyond all other makes and deadens the noise created by refrigerant moving through the system. It is from here that refrigerant exits the compressor, heading toward the condenser side that will cool it down enough for it to change phase from gas to liquid. And that won't freeze at the temperatures used to freeze food. The ideal refrigerant will have a certain set of characteristics. First, its intermolecular attraction must be weak enough that it takes little heat to force molecules apart at normal operating temperature and pressure. Second, its freezing point must be well below the lowest temperature that we want to achieve. And it must be hardy enough to undergo the phase change repeatedly and indefinitely. The first refrigerant that Frigidaire used was sulfur dioxide. Then Frigidaire engineers developed a new refrigerant, R12, also known as Freon. It was chlorine-based and contained mineral oil to provide lubrication for the compressor. R12 became the industry standard for years until the environmental effects were discovered. Today, R134A is the industry standard refrigerant for refrigerators and freezers. It contains no chlorine and uses ester oil to lubricate the compressor. So we have a liquid that can boil, absorbing heat at temperatures that are below the temperature at which we want to store food. But after boiling, the liquid, in a gaseous state, can no longer provide any cooling. How then do we convert it back to a liquid state so that it can boil again?